Now that allows water to interact strongly with things that have actual honest-to-God charges, like ionic compounds. So as shown by this figure here, so this part here represents a grain of salt where you still got the crystal lattice, so that you've got the very, very regular arrangement of the negative chloride ions, the positive sodium ions. But the interaction with the water is quite strong once involved there, and you can kind of, this is shown here by the fact that this represents a sodium ion that is interacting very strongly with the negative end, the oxygen end of a water molecule. And conversely, here you've got a chloride ion, and that is interacting very strongly with the hydrogen atoms of other water molecules. And it turns out that these interactions between the water and the sodium ions and the water and the chloride ions is stronger than the interactions between the ions and themselves and the water molecules in themselves. So it is energetically favorable for the ions to interact with water rather than their counterparts. And because of that, the salt crystal dissolves. Or the actual term is dissociates, because these ions are no longer associated with each other. And so the ionic bonds are, again, in quotes, broken. The lattice is destroyed, so now, and these groupings of the ions and the water molecules are free to move around the solution, so now we have mobile charge carriers, and this is why the solution is conductive. Now, when you do this with salt, basically all of the salt, the entire grain, chunk, whatever, interacts with the water in this way. It dissociates, and substances that do that completely are referred to as strong electrolytes. So every ion that can be put into solution and be made mobile is. So we have mobile ions, we have a conductive solution. Now let's talk about the other example that we had in that opening picture, the table sugar, the sucrose. So this is a representation or the structure of a sucrose molecule. It has two rings joined by an oxygen. And in the solid form, these molecules have some weak attraction to the neighboring sucrose molecules, which is how the solid forms. Now this has a lot of oxygen-hydrogen bonds too, and those are quite polar like the water molecules are. So sucrose interacts with water fairly strongly, but the important thing is that it does not react strongly enough to break any of the bonds within any one sucrose molecule. The interaction is strong enough to separate the sucrose molecules from each other, but nothing further. So the stuff does dissolve in water, but there are no charged particles, no ions formed in this process. So there are no mobile charges, so that solution is not conductive. It's a non-electrolyte. All right, so now let's talk about what is actually in these species now. And so this is kind of a review. So a sodium chloride solution and things like it would actually be composed of what we call our hydrated ions, so ions that are interacting, I should say, with the water molecules. And this is what that AQ means, aqueous, which means simply dissolved in water. So even though that solution might be labeled sodium chloride or NaCl, there actually aren't any intact NaCl units in there at all. You know, they're all either sodium ions interacting with water or chloride ions interacting with water, and that's it. But the sucrose solution, for example, the molecules look exactly just like they did before. They weren't really affected by it. They have just been separated from their neighbors. Now, there is another way that ions can show up in a solution. And common vinegar, acetic acid, is an example of it. So acetic acid is a neutral molecule. This is the structure right here. So we've got a carbon atom with 4 hydrogen atoms attached to it. Another carbon atom that has an oxygen atom with a double bond, an oxygen atom with a single bond, and then a 4th hydrogen atom. And it turns out that, and this is a neutral molecule. But what you find is that if you were to do this test, that so pure vinegar, not conductive. Pure water, not conductive. But if you make a vinegar solution, you find that the solution does become conductive, although not as much as the sodium chloride solution or any other salt solution. So what's going on with that? I apologize for the white blocks here. And the answer is that acetic acid and molecules like it actually react with the water. Now, what happens is the interaction with the water weakens this bond quite a bit. And in many cases, a proton is separated away from it. So here we've got a proton, and this negative ion here called an acetate ion. And the thing is that this separation does not occur without the water. But not all of them do this, maybe 1 in a million or less than that. And this is why the solution is conductive, but not as conductive as the sodium chloride solution with the same amount of solute put in it. And things that like this that create ions, but not with 100% efficiency, are referred to as weak electrolytes. So we've got strong electrolytes like sodium chloride, we've got weak electrolytes like our vinegar here, and we have non-electrolytes like our sucrose. Remember, all of them dissolve in water, but because they interact with the water to varying extents, some of them are strong electrolytes, weak and non-electrolytes.